Hello, everybody. I'm Clark Richey, and I'm the Graph Guy. Welcome back to this week's episode. I have hopefully fixed all of the technical glitches that we had last week with the camera and the microphone. So that's a great start right off the bat. So today we're going to be talking a bit about how to query your graph database to get, the relevant information you need out of that. Before we do that, a couple quick housekeeping things. As you can see here now, as you can see, as soon as I say that I am going to have no more technical difficulties, the screen share goes wonky. And we'll go with my goodness, because it worked just fine 5 minutes ago. I am so embarrassed. So let's just change this one more time. Why is it not wanting to capture monitor 1? There we go. I don't know why I did that. My apologies. Weird technology. So, housekeeping. As you can see, our Graph Guy webpage is up and live. So here you'll have links to all of the previous episodes, as well as a little bit of extra content as appropriate. So, for example, if we go to episode 4, choosing your database, then not only do you get a great image of me apparently posing as Bugs Bunny there, which is fantastic, but the pickled cherry peppers recipe that I promised to share with you as well. So the website is up and live. Feel free to go in there, and you can leave comments as well, or whatever you need to do. Other quick housekeeping episodes, we do have some new background today in honor of tomorrow's big release of the sci-fi movie Dune. Personally, really excited. Don't know about you. And then the last bit of housekeeping, I have a quick ask of everyone, if possible, please, if you could follow the stream, even if you don't like it, if you could get people that you know maybe to follow it, just a couple of you. Here's the real reason. I have a 12-year-old daughter who finds the fact that her father is on Twitch doing technical stuff absolutely hysterical. And more hysterical to her is the fact that I have fewer followers than 10-year-olds playing video games badly. So if you could help me out a little bit and help bump my follower count up just a little bit so that I can prove to her I'm maybe slightly cooler than she thinks I might be, that would be a huge boost to my ego and really kind of help bump me up with my youngest daughter. So with that, let's get directly into how do we query our graph database. And as I mentioned in one of our earliest episodes, the unfortunate truth is, unlike a relational database where we can use the standard SQL, and yes, there are some variations on flavors of that per database, but generally speaking, there is an ANSI standard for SQL. We don't have that yet in our graph database. The W3C has empowered a working group that's been at it for over a year now to develop a standardized graph language, but it's not done yet. It's close. We hope to have it soon, but it is not done yet. So I'll look at a couple of the larger, more popular ways to do that. Two in particular, Gremlin and Cypher. But I'll focus today on Cypher, and we'll talk a little bit about why I've chosen that. So to start off, let's look at Gremlin. So Gremlin, as you can see here, is a part of a larger Apache project, the Tinkerpop project. So you can find it here at tinkerpop.apache.org. One of the things I will say for Gremlin and Tinkerpop, they have really cool looking little mascots here, a little Gremlin guy and some dogs and stuff. So Tinkerpop itself is an open source framework that provides libraries and functionalities for working with a graph database. It is based upon the Groovy programming language. Groovy, for those of you who aren't familiar with it, is sort of a dynamic language that runs on top of the Java virtual machine. And then Gremlin is essentially a domain-specific language, a DSL, so a language written in Groovy to allow you to query your database or update and so forth. And so if you go to this page, you can see some examples of what it looks like. So here, if we go to the first example, if we want to find the name of all of Gremlin's friends' we can ask our graph, hey, awesome, new follower, thank you. We can ask our graph to find vertices where they have a name property that's equal to Gremlin, and then we can traverse an outbound relationship called nose, and then traverse a second outbound relationship from the vertices that we found called nose again, and find all the values of name. So not bad. It's fairly straightforward. Definitely looks like a programming language. Doesn't look like SQL. Doesn't look like Cypher, as we can see in a moment. Looks like a programming language. So again, you can see for here, for example, you say functions like repeat and in and until. Looks a lot like a programming language because it is. So if you're a developer, particularly if you're familiar with Groovy, Gremlin might be a really nice option for you. Gremlin is supported by a number of different databases. You see them highlighting some of them here, OrientDB and Titan and BlazeGraph. There are also ways to run Gremlin and the Tinkerpop stack over other databases as well that may not natively support Gremlin. And this is a good site. It has a lot of good documentation on Gremlin, has tutorials and so forth as well. Really well supported stack. And again, really awesome icons. The one I'm going to focus on today, this one I use the most and I'm particularly fond of, is called Cypher. So Cypher was originally created by Neo4j many years ago and has since been open sourced. So this is the opencypher.org webpage where the language specification is now currently maintained. Again, as you can see here, they do reference the fact that there is a graph query language initiative in progress. You have some links to where you can go and look at that. And this gives you information about the language itself. So if you're really interested in its features or references, for example, you can look at all of that here, including, I believe here under resources, you can actually get the grammar specifications, style guides, and so forth. So Cypher is a declarative language, much more like SQL than Gremlin is. So it'll look much more familiar to people who are used to querying databases as opposed to programming. I really like Cypher for a couple of reasons. One, it's widely supported, particularly among the databases that I use the most. And two, I find it to be really, really easy to use. I find Gremlin personally to be a bit more complicated to use. It's certainly very powerful, but I like simple. I'm a big fan of simplicity. So we're going to look at Cypher today. I'll be running some Cypher queries for you on top of a Neo4j database, just so we can explore how that works. So some resources. I don't know why that shows up. Here is the Neo4j page. This is the current Cypher reference card. So if you, it's a great sort of not style guide, but a great reference guide for all of the possible, syntax and expressions that are available to you. I use it frequently. It's just nicely color-coded as well. And you can always get the current version by going here. Again, I find this to be particularly helpful whenever I'm writing any kind of Cypher. Not completely exhaustive, but very, very useful. So let's jump into it. So I've got a database and I've loaded some data. I've randomly created some data according to a model, and I'm going to briefly walk you through what that model looks like here so you have some context. So I've created customers, and they have a has relationship to an address. Okay, so customers have an address. Unfortunately, I'm going to show you in a couple of different pictures here. I couldn't easily get it all into one easy picture for you. We have items, so things that we're going to buy. This is essentially a retail model what we're going to do. Items have a brand, so things that you buy are owned by a brand. And then, of course, customers, they make a customer order. Customer orders contain customer order lines, so essentially line items, and line items have items in them. And of course, those items are connected to brands, and those customers have addresses. So this is essentially the model we'll be working with today. 6 different nodes. So these four nodes are entity types, as well as an address label that, remember, sits over here off customer, or rather an address node, and a brand node that connects to item. So pretty linear, but enough relationships there to kind of make it interesting and allow us to play with a bunch of different queries. So to start off with, I am in my local Neo4j browser. I'm not going to spend any time today going over the feature of the browser. That's not really the goal of this talk. It's just a nice visual way that I'm going to use, and anyone has access to it because it's a community project, open sourced, to look at these queries. So let's start with something pretty simple here. And I'm going to put it in a graph mode, and I'm going to make this a little bit bigger for everyone. And all right, here. So I've said, I've put in a Cypher query here, and I'm going to explain it. I said match O : customer order, return O, limit 2. So I just grabbed 2 orders. Actually make it a little smaller. There we go. And if I click on one, I can see down here the properties that are in order. So order has an order number, it's got a sale amount, and so on. Use some internal things that we're not necessarily worried about here. And what I can do in this particular browser is I can just click on them to see and expand the relationships out, just to kind of validate that data model that I told you a minute ago existed. So here, again, I can see this order contains, this is an order line. I'm going to just change the color on that so that it's a little easier to differentiate what's going on. And I can see the properties on that as a line price and a quantity. And this is a customer, and they have a gender and an ID and a marital status. And if I expand out customer, I can see they made a whole bunch of other orders. And there is an address. I'm going to color code that as well. And drag it over here so we can see their address here as well as the full address. And if I expand out that line item, there we can see that item rather. This is the order line. This is the item. Let me color code that so that we can kind of keep a little bit of sanity on here. And if I expand that out as well, we can see the brand. So just as promised, we have customers that have an address that make customer orders. Customer orders contain a line item. Line item has an item associated with it, and that item can be in a brand. So real data showing you, what that model again looks like. Let's talk a little bit about this Cypher that we wrote here. Cypher is essentially a pattern matching language. So we start out when we query by saying match, and then we put things inside of parentheses. That means we're talking about a node. So customer order is the label of the node we're looking for, called, of course, customer order. That's always comes after this colon. If I put something before the colon, I'm giving it a variable. I'm assigning any nodes that are found to that variable O. So that here I can say I want to return that variable, and I'm going to limit, in this case, my results to 2. So a very easy to read, almost natural language type of query. Match customer orders and return them, limit me to 2. Lovely. There's lots of really nice, convenient functions that we can do in Cypher. If we want to count things, so here's that same query again. I'm saying, except I'm asking for customers. So match me a customer, assign that to the variable O, and then return to me the count of all of those customers. So if I run that, we can see I have 835 unique customers in my database. Awesome. So let's look at something a little bit different. If I want to get some more information about customers. So I know that customer, we saw it before, has a property called marital status, which, yes, I did spell wrong when I created this data. And I want to know all of the distinct marital statuses that exist in my database. I don't want to know all of the marital statuses because I'll get many, many duplicates. And I don't want to sort through them or scroll through them. And if I do return o.marital status, like this, what we're going to see is I get this really giant list, right? And it's hard for me to go through this and figure out exactly what are the unique values. But what we can see is I do have the ability to return just a property from that node using a dot notation to reference that variable and then a property associated with it. And you see here we get a header, and the name of that header is the exactly what we've returned here, so o.marital status. But if I just want to find out the unique values for that, I can say, please return to me the distinct values of that o.marital status. And so now I see I only get 5 records, and the database has nicely found for me all the distinct values. So if I want to look at the demographics of my customers, this is a nice way for me to look at that across one particular axis of the data, in this case, marital status. Now, I can, of course, then use this information to pull back a subset of my customers. So I can now use that same query, but I can limit my results and say I only want to find customers where that marital status property is equal to married. I know married is a good value because I found it here. It's a string value, so I put it in single quotes. If it was a numeric value, I wouldn't have those quotes. I can use double quotes as well. You'll typically see single quotes used more often. And again, I'm going to limit this to 1. I don't want to return all of my customers. So this limit function, just as you would expect, does just exactly what you would think in terms of that. And we bring it back as a graph. And so there's my one customer. And again, you can see that that marital status is indeed married. So this ability to filter is really nice. There's 2 different ways to write this. There's this way, which, and it's really a matter of style, where you put the wheres after the match. Alternatively, you can do it a different way, and you can actually embed that inside of the match for the node itself. And I can use a nice little autocomplete, marital status. In this case, instead of saying equals, it's a colon. So this means the same thing, except I've moved the where from out of here. So this still says match me customers that have a marital status of married, assign that to the variable O, and then return to me that O and limit me to 1. So if I run that again, I get the same exact result. It's just a little different way of writing it. I use both depending upon the query that I'm writing, and I tend to pick one over the other really for readability. Sometimes in really long queries, and I want to kind of make it a little more readable, I'll embed them in here. Other times where the where clauses get more complicated and I'm perhaps adding things in or oring things, I might separate those out to make it just really clear to the reader, typically myself when I have to go back and look at it later, what exactly it is that I'm doing. They operate exactly the same way. And of course, we can use our count function as well here. So we could say, how many married customers do I have? I have 169 of them. So the where works the same with count as with return or anything else, just like you'd expect. So let's look at traversing some relationships for a moment. So let's say that I want to find customers who have made orders. So again, this is a pattern matching language. So we're going to say match C colon customer. So customer is going to be assigned a variable C. Now I'm using these dash and into these square braces. So really, I'm just drawing out that relationship. It's a really nice, almost ASCII art type of language that makes it, in my opinion at least, really easy to understand what's happening here. It looks very natural. So match customer that makes a customer order and return the count of those Cs. So relationship names, labels, go inside of brackets. We have that colon there again, just like we do inside of our node label to indicate that type. You'll see I'm not assigning a variable to this makes relationship because I don't need it. I really don't even need it here for customer order because I'm not referencing it. So I could get rid of that as well as I want if I want to. Because all I'm really caring about in my return is how many customers, the count of these. So this is going to, again, traverse from customer through the makes relationship into the customer order relationship and count up those customers for me. So if I run that, we see I get 9,841. That's an interesting number to me because if I write this query and I say, how many customer orders do I have? Whoops. I actually used the right variable. There's only 7,200 orders. But a moment ago, when I said how many customers make orders, I get a number that's bigger than that. Why is that? So there's two reasons for this, and this is a really important thing to understand. And in my opinion, it can be one of the trickier things to wrap your heads around when you're querying a graph. So because I generated this data randomly, I have some customers, or rather some orders that are made by multiple customers. Now, logically, that doesn't make any real sense, right? But I just randomly generated this data, and I didn't apply any business rules to prevent more than one customer from making the same order. So I have, in this case, a number of orders that are made by the same customer, and that is bumping this count way up high. So that's reason number one, right? I have multiple customers making the same order, but still, why does it seem so high? Well, again, we have to think about what's happening here. So if we actually have to remember that when we run a query, even though our data is in a graph, what comes back is often in tabular form. And we get a kind of a hint of that when we see that the fact that we have this table view option available to us here in the browser. So let me show you what I mean by that. Instead of saying return count C here, let me give that a relationship, or rather a variable name, and that as well. And let's return C and M and O, and I'll limit this to, let's just say 6. Okay, and let's view that as a graph. And then there we go. So right off the bat, you might be thinking, whoa, Clark, you said limit 6. I can count 1, 2, 3, 4, 5, 6, 7. I see 7 things. Something's not right. Well, yes and no. The data is absolutely right. It did exactly what I asked. What we have to remember, this goes back to what I said a moment ago, this really comes back as a table. So let me make this a little bit bigger. And let's look at this as a table view. So when the database traverses this query, it does exactly what we asked it to do. It finds customers who have a makes relationship to a customer order, and it returns those. And when it hits 6, it stops. So let's see what we get. So we get this first customer here, who is customer 64334, and has this particular relationship here to a customer order 27648. Okay, so that's 1. But this same customer now makes a different relationship. Again, the identity is different to a different order number. That's 2. Same customer, different relationship, different order. 3. Same customer, different relationship, different order. 4. Same customer, different relationship, different order. 5 rows. Same customer, different relationship, different order. 6 rows. So we are getting a limit of 6 back. It's that when we view them or think about it in this graph view, as opposed to a table view, it looks like we're getting back an odd number. But we have to remember again, that's 1, that's 2, 3, 4, 5, and 6. That's one of the hardest concepts, in my opinion, to really wrap yourself around, particularly when you have more complex queries. And your counts might not, or your results might not be exactly what you think they are. A really good tip is make sure to look at that response as that actual tabular response that comes back, the data that comes back. Think about it as a graph, absolutely. But remember, it does come back in rows and columns, oddly enough. And that makes all of the difference. All right, so we've now gone ahead and we've showed how to walk some relationships. We've talked a bit about binding variables to different names and so on. Let's hit a couple more interesting examples as well. Oh, and so to back to original example. So if we actually now count again those distinct customers that make these orders, we'll see there's 835 distinct customers making orders. That matches our customer counts, or rather, much more closely, as well as our orders. This is a number that makes sense because I'm removing those duplicate customers here by using that distinct. So I can place the distinct keyword inside of my count to only count unique values of that customer. So again, a really, really nice thing to be able to do there. All right, so let's look at walking a bit of a longer relationship. So, and it helps if I grab the rest of the query. All right, so I want to walk all the way from my customer to the item that they purchased. So I'm going to go from customer makes a customer order that contains a customer order line, which has an order for an item. And I want to know, for example, what are all of the item descriptions that have been ordered? So this first part of the query should look pretty similar to what we've done before, except I've added a few more steps along the way. One thing I didn't mention before, you'll notice that there are little arrows on here. Again, those are simply created with the dash and the greater than sign. In the browser here, it kind of makes it into a pretty arrow for you, but it is just a dash and a greater than sign. The arrows do indicate the direction to traverse. You can traverse, even though I know that the customer relationship does go from customer to customer order. I can traverse it the other direction if I want to. I can also leave this direction out of the query, which will tell the database to query this in either direction. However, that is significantly less efficient in terms of performance because the database has to look at things in more than one direction potentially. So if I know the direction of my relationship, it really helps my performance to include that in my query. And in my opinion, it also, again, makes your queries much more readable. So here, we're introducing the order by. So I'm going to give me my distinct item descriptions, just like I did for marital status before. In this case, I want to order them. I want to order them by that item description, and I'm going to limit them to 10. So let's just see the first 10 item descriptions that I have. And here you see I have aerodynamic aluminum bench and a lot of aerodynamic things. Again, randomly generated data. I can, of course, use that information now to find customers who have ordered things that are of a particular type. So here I'm saying, find me customers who've made those orders that contain customer order lines for orders where, again, that item description is aerodynamic aluminum table. I hope someone actually makes an aerodynamic aluminum table. And I could count how many orders there are. So how many orders are actually, contain that aerodynamic aluminum table. Again, I'm going to limit it to distinct orders because some orders might contain more than one aluminum table, and I don't want to count them twice because it's just one order. So here I can say I have 2 orders for that aerodynamic aluminum table. Excellent. So what if I want to do something which is, I think, really fun and easy to do in graph databases that can be really hard to do in relational databases, and that is I want to do grouping. So let's get to grouping in just a moment. Before we do grouping, let's look at one more intermediate step. And here I want, actually, we're going to go right to grouping. So I'm going to find customers who make orders. And I want to get back, essentially what I want to know is who made the most orders. Which of my customers made the most orders? So I'm looking for potentially my most valuable customers here. So I'm asking it to return to me the distinct customer ID. Now I'm going to use a new term here, just introducing is this as. So I want to essentially rename c.id on my return as customer ID, purely for readability. So give me the distinct values for that customer's ID field, called customer ID, and also give me the count of that O variable, which is my customer orders, and call that number of orders. And then I want you to order this by the number of orders. I want to do it descending, so I want the most orders first, and I just want the top 20. So this is really great. You notice I don't have to use the word group in here at all. Intrinsically, in the graph database through Cypher, it understands that when I'm grabbing these, that when I'm taking the customer's ID and the count of something else, 2 of the things that are in the same statement, that I want to group them. So that's going to happen automatically for me. So let's go ahead and run this. And we see here that, as promised, customer 6 has made 151 orders, customer 1, 140, 8's 140, and so on. So this implicit grouping is really, really handy. It makes it, again, it's just the ability to do some fairly complicated queries in a really simple, highly performant way. Just bear in mind that this grouping will automatically happen. If I were to add a third property here, then I'm probably going to get results that I did not expect because of the way grouping works. So I don't want to go into too much detail on that because we're running a bit low on time. But just be aware of intrinsic grouping. It's a really great feature. And then lastly, I just want to show you. So this is the easiest way to write that query, right? I don't care about what items are in this order. I just want to know who makes the most orders. To kind of come back to a point we made earlier, if I were to write out that entire sort of chain from customer all the way back through to item again, and then still do the same thing, say return my distinct customer ID and my count as O of number of orders. Let's see what I actually get here. Wow, so now we see I get a huge number of orders. I get customer 1 is ordering 1,400 orders. Why is that again? It's back to what we talked about earlier. We have to remember that this is coming back in tabular view. So if a customer has an order that has multiple items, as many of them will, because this order line can have an order to more than one of these items, it's going to count that again and again and again, because the same order will be counted more than one time. Because it's going to return one row that brings us down from customer all the way through the first item in the order, then another row that's going to have the same order, a different order line to a second item. And so we're going to double count that order. So I would have to say distinct O. And now if I do that, you see we get exactly the same results that we did before, 151, 140, 140, and so on, because we've removed that double counting of these O's. So again, when I say earlier, remember, things come back as rows and columns. That's really important when you're writing more complex queries, such as this one, where you kind of have to remember that there could be multiple branches on this that all roll up essentially off of the same node here that you might be counting or doing some aggregation on. So this has been a really brief, high-level introduction to querying graph databases, particularly in Cypher. For more information, if you go here, I highly recommend the Neo4j Graph Academy. There is really good free online training on querying using Cypher. And certainly, if you're more interested in Gremlin Tinkerpop, then the Apache Tinkerpop site also has a really great set of tutorials on there. So I hope you've enjoyed today's talk. Really looking forward to your feedback. Please subscribe. Please recommend to others. Show my daughter I'm cooler than she thinks I am. And hopefully I will see you next week. I'm Clark Richey, and I'm the Graph Guy.